Hello, and welcome back to The Glow Show, the show where everything glows. We've had technical difficulties for the last 6 years, but we're finally back on track, and we're ready to begin doing episodes again. So this week, we're talking a little bit about radium. Now, radium is a chemical element with the symbol Ra and atomic number 88. It is the sixth element in group 2 of the periodic table, also known as the alkaline earth metals. Pure radium is silvery white, but it readily reacts with nitrogen rather than oxygen on exposure to air, forming a black surface layer of radium nitrate, Ra3N2. All isotopes of radium are highly radioactive, with the most stable isotope being radium-226, which has a half-life of 1600 years and decays into radon gas, specifically the isotope radon-222. When radium decays, ionizing radiation is a byproduct which can excite fluorescent chemicals and cause radioluminescence. Radium in the form of radium chloride was discovered by Marie and Curie in 1898 from ore mined Jacmov. They've extracted the radium compound form uranium nitrate and published the discovery at the French Academy Sciences 5 days later. Radium was isolated in its metallic state by Marie Curie and André Louis Debrane through the electrolytes of radium chloride in 1911. In nature, radium is found in uranium and, to a lesser extent, thorium ores in trace amounts as small as a seventh of a gram per ton of urine nitrate. Radium is not necessary for living organisms, and adverse health effects are likely when it is incorporated to biochemical processes because of its radioactivity and chemical reactivity. Currently, other than its use as nuclear medicine, radium has no commercial applications. Formerly, it was used as a radioactive source for radioluminescence devices and also in radioactive quackery for its supposed curative powers. Today, these former applications are no longer in vogue because radium's toxicity has become known and less dangerous isotopes are used instead of radioluminescent devices. And there you have it. That's all we know about radium. Oh, I think there's actually a little bit more here. Bulk properties. Radium is the heaviest known alkaline earth metal, and it's the only radioactive member of its group. Its chemical and physical properties are closely resembled to lighter congener barium. Pure radium is a volatile silvery white metal, although its lighter congeners calcium and strontium and barium have a slight yellow tint. The tint rapidly vanishes on exposure to air, yielding a black layer of radium nitrate, Ra3N2. Its melting point is either 700 Celsius, 1292 Fahrenheit, or 9607 Celsius, 1760 Fahrenheit, and its boiling point is 1737 Celsius, 315 circle F. Both of these values are slightly lower than those barium conforming periodic trends on the group 2 down to the group 2 elements. But like barium and the alkaline metals, radium crystallizes in the body-centric cubic structure at a standard temperature and pressure. The radium-radium bond distance is 514.8 picometers. Radium has a density of 5.5 G/C3 cm3, higher than that of barium, again confirming periodic trends. The radium-barium density ratio is comparable to the radium-barium atomic mass ratio due to the two elements similar crystal structures. Radium has 33 known isotopes with mass numbers from 202 to 234, all of them radioactive. Four of these are a half-life 11.4 days, are a 3.64 days, are 226 RA 1600 years, and 228 RA. That was just to clarify, 223 RA half-life 11.4 days, 224 RA is 3.64 days, 226 RA is 1600 years, and 228 RA is 5.75 years. They occur naturally in the decay chains of primordial Thium-232, uranium-235, and uranium-238, although 223 RA from uranium-235, 26 RA from uranium-238, and the other two for thorium-232. These isotopes nevertheless have half-lives too short to be primordial radionuclides and exist in nature from these decay chains. However, with the together with the mostly artificial 225 RA 515 days, which occurs in nature as a decay product of minute traces as 237 NP. These are 5 most stable isotopes of radium. All other known isotopes have half-lives under 2 hours, and the majority have half-lives under a minute. At least 12 nuclear isomers have been reported. The most stable of them is radium-205M, with a half-life between 130 and 230 milliseconds. This is still shorter than the 24 ground state radium isotopes. This is in the early history of the study of radioactivity. The different natural isotopes of radium were given different names. In this scheme, 223Ra was named actinium X ACX, 224Ra thorium X THX, 226Ra radium Ra, and 228Ra mesothorium 1 MTH1. And it was realized that all of these isotopes of the same element have many of the names just fell out of use, and radium came to refer to all isotopes, not just 226Ra. Oh, okay. Some of the radium's 226 decays products received historical names under radium, ranging from radium Ra to radium G, with the letter indicating approximately how far they were down the chain from their parent 226Ra. Radium emanation equals 222Rn, RAA 222Rn, RAA equals 218PO, RAB equals 2. Radium emanation equals 222Rn, RAA equals 218PO, RAB equals 214PB, RAC equals 214BI, RAC1 equals 214PO, RAC2 equals 210 Ti, RAD equals 210 PB, RAE equals 210 BI, RAF equals 210 PO, and RAG equals 206 PB. 226 RA 226 RA is the most stable isotope of radium, and it's the last isotope in the 4n+2 decay chain of uranium 238 with a half-life of over a millennium. It makes up almost half of natural radium. It is 2.7 million times more radioactive than the same molar amount of natural uranium, mostly uranium-238, due to its proportionately shorter half-life. A sample of radium metal maintains itself at a higher temperature than its surroundings because of the radiation it emits: alpha particles, beta particles, and gamma rays. More specifically, natural radium, because it's mostly 226 Ra, emits mostly alpha particles, but other steps in its decay chain, the radium or radium series, emit alpha or beta particles, and almost all of the particle emissions are accompanied by gamma rays. In 2013, it was discovered at CERN that the nucleus of radium-224 is pear-shaped using a technique called Coulomb excitation. This was the first discovery of an asymmetric nucleus. This is a strong circumstantial evidence that certain heavy, unstable atomic nuclei have distorted nuclei, in this case a pear shape. Radium, like barium, is a highly radioactive metal and always exhibits its group oxidation of +2. It forms the colorless Ra2+ cation in aqueous solution, which is highly basic and does not form complexes readily. Most radium compounds are therefore simple ionic compounds, though participation from the 6s and 6p electrons in addition to the valence 7s electrons is expected to relativistic effects and would enhance the covalence character of radium compounds such as RAF2 and RAAT2. For this reason, the standard electrode potential for the half reaction Ra2 plus AQ plus 2E RAS is minus 2.916 V, even slightly lower than the value minus 292 V for barium, whereas the values have previously smoothly increased down the group. Ca minus 2.84 V, SR minus 2.89 V, Ba minus 2.92 V. The values for barium and radium are almost exactly the same as those of the heavier alkali meets potassium, rubidium, and cesium. Compounds. Solid radium compounds are white as radium iron provides no specific coloring, but they gradually turn yellow and then dark over time due to self-radioless from radium's alpha decay. Insoluble radium compounds co-appreciate with all barium, most strontium, lead, and most lead compounds. Radium oxide, RaO, has not been characterized well past its existence, despite oxides being common compounds for other alkaline earth metals. Radium hydroxide, Ra, HOH2 is the most readily soluble with the alkaline earth hydroxies and has a stronger base than barium congener, barium hydroxide. And it's also more soluble than actinium hydroxide and thorium hydroxide. These three adjacent hydroxides may be separated by precipitating them with ammonia. Radium chloride, RaCl2, is a colorless luminous compound and becomes yellow after some time due to self-damage by the alpha radiation coming off of radium when it decays. Small amounts of barium impurities give the compound a rose color, and it is soluble in water, although less so than barium chloride. Its solubility decreases with increasing concentration of hydrochloric acid. Crystallization from aqueous solution gives the dihydrate RaCl2,2H20 isomorphous with its barium analog. Radium bromide is also a colorless luminous compound. In water, it's more subtle than radium chloride. Like radium chloride, crystallization from aqueous solution gives the dihydrate RaBr2,2H20 isomorphous with its barium analog. The ionizing radiation emitted by radium bromide excites nitrogen molecules in the air, making it glow. Well, there you go. The alpha particles emitted by radium quickly gain 2 electrons to become neutral helium, which builds up inside and weakens radium bromide crystals. This effect sometimes causes the crystals to break or even explode. Radium nitrate is a white compound that can be made by dissolving radium carbonate in nitric acid. As the concentration of nitric acid increases, the solubility of radium nitrate decreases, an important property for the chemical purification of radium. Radium forms much of the same insoluble salts of its lighter congener barium. It forms the insoluble sulfate, RaSO4, the most soluble known sulfate. Chromate, RaCrO4, carbonate, RaCO3, iodate, RaIO3, tetrafluoroberylate, RaBeF4, and nitrate, RaNO3, With the exception of the carbonate, all of these are less soluble in water than the corresponding barium salts, but they are all isostructural to their barium counterparts. Additionally, radium phosphate, oxalate, and sulfate are probably also insoluble as they co-precipitate with its corresponding insoluble barium salts. The great insolubility of radium sulfate at 20 Celsius, only 2.1 mg, will not dissolve in 1 kg of water. That means that one of the less biologically dangerous radium compounds, the large ionic radius of Ra2 plus 148 pm, results in weak complexion and poor extraction of radium from aqueous solutions when not at a high pH. All isotopes of radium have half-lives shorter than the age of the Earth, so that any primordial radium would have decayed a long time ago. Radium nevertheless still occurs in the environment, as the isotopes 223Ra, 224Ra, 226Ra, and 228Ra are part of the decay chains of natural thorium and uranium isotopes. Since thorium and uranium have long half-lives, these daughters are continuously being regenerated by their decay. Of these 4 isotopes, the longest lived is 226Ra, half-life 1600 years, a decay product of natural uranium because of its relative longevity. 226Ra is the most common isotope of the element, making up about 1 part per trillion of the Earth's crust. Essentially, all radium is 226Ra. Thus, radium is found in tiny quantities in the uranium or uranium nitrate and other varieties of the uranium minerals, and even in tinier quantities in thorium minerals. 1 ton of pitch blende typically yields about 1/7 of a gram of radium. 1 kilogram of the Earth's crust contains about 900 picograms of radium, and 1 liter of seawater contains about 89 femtograms of radium. Oh, there you go. History. Radium was discovered by Marie Skłodowska-Curie and her husband Pierre Curie on December 21st, 1898, in a uraniate pitch blende sample of Yakimov. While studying the mineral earlier, the Curies removed uranium from it and found that the remaining material was still radioactive. In July 1898, while studying pitch blende, they isolated an element similar to bismuth, which turned out to be polonium. Then they isolated a radioactive mixture consisting of 2 compounds of barium, which gave a brilliant green flame color, and unknown radioactive compounds, which gave carmine spectral lines that they've never documented before. The Curies found the radioactive compounds to be very similar to the barium compounds, except that they were less soluble. Well, that makes sense. This discovery made it possible for the Curies to isolate the radioactive compounds and discover a new element in them. Curies announced their discovery to the French Academy of the Sciences on December 26, 1898. The naming of radium dates back to about 1899, and from the French word radium, formed in modern Latin from radius, ray. This was the recognition of radium's power emitting energies in the form of rays. In September 1910, Marie Curie and Louis Anderson de Boyne announced that they had isolated radium as pure metal through the electrolytes of pure radium chloride, Ci2, solution from a mercury cathode, producing radium mercury amalgam. This amalgam was then heated in an atmosphere of hydrogen gas to remove the mercury, leaving pure radium metal. Later that same year, E. Euler isolated radium by thermodecomposition of its azide, Ra(N)(3)2. Radium metal was the first industrially produced at the beginning of the 20th century by Brekeco. A subsidy company, Union Minière du Haut-Katanga, an oil plant in Belgium. The general history unit for radioactivity, the Curie, is based on radioactivity 226Ra. The amount of radioactivity released by 1 gram of radium is equivalent to 1 Curie. And I think that there you have it. That's all you gotta know about radium. We'll be back another time to talk about another thing that actually, there's actually a little bit more here, so we will continue going. Radium was formerly used in there's a little bit more here, so we're gonna just keep going. Radium was formerly used in self-luminous paints, watches, nuclear panels, aircraft switches, clocks and instrument dials. A typical self-luminous watch that uses radium paint contains around 1 microgram of radium. In the mid-1920s, a lawsuit was filed against the United States Radium Corporation by 5 dying radium girls, dial painters who have painted radium-based luminous paint on the dials of clocks and watches. The dial painters were instructed to lick their brushes to give them a fine point, thereby ingesting radium. Their exposure to radium caused serious health effects, which included sores, anemia, and bone cancer. This is because the body treats radium as calcium and deposits it in the bones, where radioactivity degrades marrow and can mutate bone cells. During the litigation, it was determined that the company's scientists and management had taken considerable precautions to protect themselves from the effects of radiation, but it did not seem to protect their employees. Additionally, for several years, the companies had attempted to cover up the effects to avoid liability, and insisting that the radium girls were instead suffering from syphilis. This complete disregard for employee welfare had a significant impact on the formulation of occupational disease labor law. As a result of the lawsuit, the adverse effects of radioactivity became widely known, and radium dial painters were instructed in proper safety precautions and provided with protective gear. In particular, dial painters no longer licked paintbrushes to shape them, which caused some ingestion of radium salts. Radium was still used as dials in the late 1960s, but were no further injuries to dial painters. This highlighted that the harm to the radium girls could have been easily avoided. I think that's all you need to know about radium. I hope you all have a great day, and we'll see you next week.